This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, the professor for this class. And this is Lecture 68, Part 2 of a two-part series on directed self-assembly. Today we're going to talk about self-assembly. The next lecture, we'll talk about how we direct that self-assembly, which makes the phenomenon of self-assembly useful from a micro-patterning perspective, a lithography perspective. So what is self-assembly? It's basically an arrangement of molecules that takes advantage of or uses different properties of the molecule on different sides of the molecule. That is an orientation dependence. The most common example is if I have a molecule where one side of it is polar and the other side is nonpolar. Very different properties. But it could be more than just polar and nonpolar. But the idea is you have a molecule of a certain shape, but because of the very different properties on the different sides, it arranges itself or self-assembles in particular ways. There are very common examples of self-assembly and not so common examples. Maybe the most common, the one that we see almost on a daily basis, is the impact of surfactants when it interacts with water and forms bubbles. Less common is block copolymers, which will be the subject of most of the lecture today. But let's start with something very common. Let's look at bubbles. What is a bubble? How does it form? Bubbles form from surfactants, and surfactants are long molecules with different kinds of ends. A very common example is sodium lauryl sulfate, or a variation of it, ammonium lauryl sulfate, which is the active ingredient in almost all shampoo. It's basically a detergent, and what that means is it's got a long lipid end, a hydrocarbon, long chain, and then on the other end it's a salt. So we have a polar end and a non-polar end. These two ends provide the different properties that we need, both for a surfactant and for self-assembly. In this case, one end's polar and the other is non-polar, so if we put it in water, the polar end likes to be in the water, and the non-polar end sticks its tail out the interface. So surfactants tend to line up at the interface between water and air, or water and other materials. But they can also self-assemble in a different way. This is a micelle. A micelle is a construction of these surfactants where there's a high enough concentration, called the critical micelle concentration, where the surfactants find each other, and all of the tails, the lipid ends of the surfactant, interact with each other, having an outside region that's all polar, and if the outside world is water, let's say, then this will be a more energetically favorable, a more stable configuration of the surfactants. This is how detergents end up working, where the lipid end likes the grease of a greasy plate or your hair, and the polar end likes the water, which is an excellent solvent for almost everything except grease. By surrounding the greasy molecules with the surfactant, we can dissolve those oils into the water. It's also how soap bubbles are formed, where again the polar end likes the water and the lipid end doesn't, so it sticks out into the air. We form an interface which can be quite thin, the soap bubble. So this kind of self-assembly is very common, but we're going to look at a different kind that we're going to engineer to be the way we want. And that self-assembly will use block copolymers. So to understand what a block copolymer is, let's look at what a copolymer is first. We probably all know what a polymer is. We've talked about polymers in this class. Polymer is a one monomer unit that repeats many, many times. Well, a copolymer is derived from two or more monomers. So if we have just one monomer that repeats many, many times, we call that a homopolymer. But if we have more than one monomer unit that connect up together into a long chain, we call it a copolymer. So here I have two monomers, I call it A and B, and they connect up in a long chain that keeps going on both directions. And there's a ratio of X to Y of the number of A's to the number of B's in this long chain. But in general, the positions of A and B are completely random, unless we do something very special, which takes extra work, extra effort on our part when we make this polymer. These A and B monomers will just be randomly dispersed along the chain. Therefore, the only thing we need to know to describe the copolymer is the relative fractions of A and B, the fraction of A and the fraction of B, Fa and Fb, for example, and then the molecular weight. If we know those things, then we know what the copolymer is. Of course, we can have more than just two monomeric species combining to make a copolymer. You could have three or more as well. Well, a block copolymer is a special kind of copolymer where the positions of the two blocks, the two monomers, are not random. In fact, we create them such that all the A is connected to itself in what looks like a homopolymer group, and then all the B is connected to itself, and then we have one connection that connects the A to the B. Generally, we take, for example, I'll use an example of polystyrene block polymethyl methacrylate, PSB, PMMM. PMMA is how we would write it. We start by forming polystyrene. So have a monomer, and then we attach another monomer to it, and then another monomer, and then another monomer, and we start growing this chain of polystyrene. Then we change the ingredients. We still have a reactive end on our polymer, but now we start adding PMMA, or MMA, the monomer piece, and it attaches to the polystyrene piece. And then more MMA monomers attach onto that, and they keep growing. The result is block copolymers. One block of A connected to a block of B. So a very distinct arrangement. There's, of course, more than one way to do this. If we have two monomers, the simplest is this A-B approach I just mentioned in a linear chain. So we have a chain of A and then a chain of B. But we could have an A-B-A configuration. We could put the B in the middle, A on either side. And we could repeat that multiple times. Or we could branch them out in different ways. Of course, we could have three or even more monomers connected together, and then the configurations get more interesting. We're going to focus only on the simplest connection, one A connected to one B in a linear arrangement. What makes block copolymers interesting, at least from our perspective, is that they can undergo microphase separation. Let's explain what that means. Well, if we look macroscopically, if we have a big bottle of this copolymer, this block copolymer, then macroscopically it's well mixed. I mean, the two A's and B's are all connected to each other, so you're not going to have any macroscopic separation where all the A floats to the top and all the B sinks to the bottom. Something like if you had oil and water mixing or not mixing. That can't happen because every A is connected to a B. But we can get microphase separation. Suppose I have A that likes to be around other A's but doesn't like the B. Right? So the A is, say, polar and the B is nonpolar. If they have a high energy of mixing, that is, they don't like to mix, then they'll rearrange themselves to form the lowest possible energy. And that rearrangement means the A will be next to an A and a B will be next to a B. This arrangement, which we call self-assembly, is driven by the chemical incompatibilities. Right? The fact that an A next to a B is higher energy than an A next to an A. Kind of like a surfactant. They can form micelles, they can form layer films like the bubbles that we saw, but also more complex patterns can result as well. And we'll look at some of those complex patterns. Our example, polystyrene is nonpolar, polymethyl methacrylate, PMMA, is polar, and so they don't like each other. This microphase separation for a simple linear diblock copolymer looks something like this. We start with, say, A block B, and then we bring another A block B by it, but the A and the B doesn't like each other, right? These two guys don't like each other. So if we supply a little bit of energy, like we heat it up so that it's enough energy for these molecules to move around, well, then that molecule will flip and rearrange itself so that the B's are next to each other, because that's a lower energy configuration. B's like each other, A doesn't like B. It happens not just with two block copolymers, but with lots of them. And so we'll get layers of A's and B's, where the B's line up next to the B's and the A's line up next to A's, and this will continue on repeatedly in arranging itself in this fashion. Well, given the size of these molecules, we find, and some other aspects, some other properties, we find that there is going to be a specific distance or pitch called L0 that separates the domains. So here we have a domain of A, a domain of B, and then another domain of A, and then another domain of B will be next to it and repeats. And the repeating distance is called L0. This is the natural period of the microphase separation for the block copolymer. For polystyrene block PMMA, this L0 can be anywhere from about 25 to 80 nanometers, and we'll talk about what properties of the polymer determines what this repeating natural period is. Here is a picture of a block copolymer coated on a substrate, and this is a very characteristic kind of a period of self-assembly of these block copolymers, and it looks like, from top down, like a fingerprint. We've actually done some, after we've coated this, we've actually etched away one of the blocks so that we could see the arrangement. Coat the whole thing with the block copolymer, anneal it so that it arranges into the lowest energy configuration, and then put it in an etch that preferentially etches, say, the polystyrene but not the PMMA, or the other way around. You find these characteristic patterns that look like fingerprints. This is microphase separation. Notice that even though the directions of these things are kind of meandering, the period here is always about the same. It's that characteristic natural period, and it will always assemble into that period. One of the key parameters that controls this self-assembly is the Flory-Huggins Interaction parameter. Now, if you've had thermodynamics, you may recall learning about the Gibbs free energy of mixing. If I mix two things together, that might result in a lower energy or a higher energy than when they're separate. And it depends upon this Gibbs free energy of mixing. So if I have a certain number of moles of a certain substance and a volume fraction Phi1 rather, of the solvent, and then a number of moles N2 and a volume fraction Phi2 of the polymer, the Gibbs free energy of mixing goes like this. R is the universal gas constant, T is the absolute temperature. But this standard free energy of mixing doesn't take into account the different properties of polymer versus solvent. And in particular, it doesn't take into account the interaction of the solvent and the polymer. If the polymer, which often has a much, much bigger molecular size than the solvent, is taken into account, we have to add an extra term that has Chi12 included. Chi12 is the interaction parameter between the solvent 1 and the polymer 2. And this takes into account the energy of interdispersing, the energy required to interdisperse the polymer and the solvent together. Now that might be a positive number or it might be a negative number depending on whether the solvent likes the polymer or not. So what determines this interaction parameter? If I have two blocks A and B in a block copolymer, the interaction parameter from A to B is given by this equation. K is the Boltzmann constant, T is the absolute temperature. The main term is delta W, the energy change or the free energy cost of an A interacting with a B compared to an A interacting with an A or a B interacting with a B. In other words, if I put two A's together, it requires a certain amount of energy. But if I flip it around and put an A next to a B, that requires a different energy. So delta W is the energy cost associated with switching from an AA interaction to a AB interaction. Z is the coordination number that is having to do with the geometry of these polymers. So if I have a whole collection of block copolymers and I take one of these AB block copolymers and I rotate it 180 degrees, well, how many different AB interactions are affected by that? I'll certainly have the one to the left, but I also have the one to the right. I might have one above it and one below it. It's often something like 4 interactions that change, but it can be more or less depending on the configuration of the block copolymers. All of these things together determine the Flory-Huggins interaction parameter for that particular block copolymer. If it's positive, if chi AB is positive, then there's a net repulsion between A and B. If I have a negative value, that means putting an A next to a B results in a lower energy, and there's a free energy drive towards mixing them up. And it can be either way, but we're going to design block copolymers where chi AB is positive. In fact, we're going to try and make it a positive and large positive number. So this Flory-Huggins interaction depends not only on the AB interaction, but also the length of the chain. You can imagine if I had 5 monomers connected together of A and another 5 of B, that if I rotate this polymer around, then I'll have 5 times as many interactions of A's and B's than I had before. So I'll have to take this chi number and multiply it by the number of monomers in the diblock copolymer. And that turns into the total driving force, the total energy of that changing interaction. And what people have observed theoretically is that we can start getting microphase separation whenever that quantity is bigger than about 10.5. Now experimentally, we find that we tend to get microphase separation when this number is larger than this, maybe closer to 15 or 20. But certainly it has to be bigger than 10.5, and that's based on some modeling that people have done. So it's the magnitude of chi times n that determines whether microphase separation is going to occur. A larger value of chi times n is a much greater driving force towards microphase separation. And if chi times n is too small, then I won't get microphase separation. Everything will remain mixed and disordered. Now, with all of that said, let's go back to the natural period. The natural period says how these things arrange themselves, and we find that there's a very simple expression for that natural period derived based on the modeling work, and it has 3 pieces. It has A, the monomer size, chi, the Flory-Huggins interaction parameter, and N, the number of monomer units strung together to make a diblock copolymer. And with the certain powers, you can see that we can predict what this L0 is. Next lecture, we'll talk about resolution, that is, trying to make L0 smaller and smaller, how we actually go about doing that. Last topic to think about, phase diagrams. what do we have? If we're making up one of these polymers, we have a specific A and a specific B. There's two things that we can vary. We can vary the total number of monomers strung together to make a chain. That's N. We can also adjust the fraction of that copolymer that is A compared to B. We don't have to have exactly 50-50. 5 monomers of A connected to 5 monomers of B, for example, to give N equal to 10 and FA of 0.5. We don't have to do that. We could have 3 monomers of A connected to 7 monomers of B. So this fraction of A and the fraction of B can be varied as well. So if we were to vary these things, change N, change FA, and then look at what we mix these things up and look at what happens, we find that they can be organized in terms of a phase diagram. We plot the boundaries between the phases on a chi-N versus FA graph and get our results. Our results will depend on substrate properties and film thickness, which we're going to talk about next. But let's ignore that for a minute and just think about these two quantities. Whoops. Sorry. Here I have chi-N, where I've made it bigger by making N larger and larger. And then I have FA, where I changed the fraction of A versus the fraction of B. So this is pure pure B on this side, and here's pure A on the right. And then I plot the boundaries between different phases, that is, different organizations that happen. And I find out, for example, here's a region that is labeled S, where I get a spherical configurations. Here the black is the A and the red is the B. So I have a little bit of, if I have a little bit of A and mostly B, the A will just associate with itself and form this spherical shape. On the other hand, here's an S prime region shown here, where I have, I guess I said that backwards, didn't I? Yeah, B is the black and A is the red. So over here in this S region, it's mostly the red, mostly B present, and then the A groups up in little spheres. In the S prime region, I have mostly A. So you see I have, say, 90% A, and it organizes into big regions of A with little bits of B in the circles. On the other hand, so I might get, for example, this region called L, that stands for lamella. And if I have 50-50 A and B, and I have a high enough chi times N, it'll form these lamella, where I have a region of A, a region of B, region of A, region of B, all just piled up on top of each other. I can get these gyro kinds of arrangements as well. I can get cylinders, lots of different possibilities. So this is a theoretical arrangement. When chi times N is less than 10.5, I always get disordered mixing. Here's an experimental result for a particular black copolymer system, and you can see it's not quite as pretty as the theory says, but nonetheless we do get this phase separation. Note that we have to have more like 17 or 18 chi-N critical value before I get any ordering at all. So phase diagrams are very useful for understanding how these things interact. But there's another piece of the puzzle too, which is the interfaces and the thickness of the film. So let's look at the effect of the film thickness. Whenever I try to coat this film onto a substrate, my film thickness is very, very small. If it's less than L0, the natural period, what happened is the microdomain formation becomes frustrated. It just doesn't have enough room to rearrange itself. Even if I anneal it to let it move around and find its lowest energy configuration, if I don't have a thick enough film, I can't rearrange and I get no phase separation. Now when T is much, much bigger than L0, then other complicated things can happen. What I do is generally get layers of an L0 group on top of an L0 group. on top of another L0 group. But I might not get the exact same number of layers. So I might get one region where I get, one extra layer compared to another region, so I get a step height of L0. And here is an actual AFM plot of some material that was coated, and you see these domains where it's one step height shorter in certain places compared to another. Well, for our purposes, this is not going to be very interesting either. So we're not interested in thicknesses that are much, much smaller than L0, and we're not interested in thicknesses that are much, much bigger than L0. Instead, we're going to be interested in thicknesses that are just about equal to L0, the natural period of our block copolymer. This will be the regime of interest for lithography, and now the way it will arrange, if we have a thickness of about L0, will depend on the interfacial energies, mostly with the substrate, but also with the air as well. So here I show a couple of different configurations depending on the energy of the substrate. So if the substrate has a particular configuration where the red material, likes that, well then the block copolymers are going to stand up straight with the A on the bottom and the B on the top. The result will be lamella such that I have a whole layer of nothing but A, and on top of it is a layer of nothing but B. All right, so I'll get this layering. So when the copolymer stands up straight, the layers that are formed are horizontal layers, or lamella. On the other hand, if I had a substrate that really likes the B, I'll get the same thing but upside down, where all the B is attached to the substrate. On the other hand, if I have a neutral substrate, that is, a substrate that doesn't prefer A or B, it's not polar, it's not nonpolar, it just doesn't care, then the most energy efficient configuration will be the polymers laying down flat, A and the B touching the substrate, and so I'll get these vertical domains, a whole domain of A and a whole domain of B, so we call these vertical lamella. This is often the configuration we're looking for, but not always. Sometimes we want one of these other configurations instead. Now, I mentioned annealing a few times. In order to get this rearrangement to occur so that the block copolymer finds its low energy state, we have to anneal it. Two ways of annealing. One is to use evaporation as a mechanism of slowly allowing things to configure themselves. If we put the polymer in a solution, it tends to be very mobile, and then we slowly evaporate to allow it to settle down into a lowest energy configuration. This is somewhat difficult to control and tends not to be as useful, but a thermal annealing is often a better. We can achieve an equilibrium. It is slow, and there's not very many degrees of freedom to affect the morphology, that is the shape and the structure of the block copolymers after they've rearranged themselves. But nonetheless, thermal annealing is almost always the preferred approach to allowing the block copolymers to rearrange themselves into the lowest energy configuration. All right, let's look at what we've learned so far in Lecture 68. Why does molecular self-assembly happen? What is a copolymer? What is a block copolymer? Explain microphase separation. What is the Flory-Huggins interaction parameter, interaction parameter, and what does it tell us? And finally, what are the factors that determine the morphology of self-assembled block copolymers, the shape and the structure of these copolymers? Well, that's our lecture on self-assembly. Next time we'll learn how to direct that self-assembly to create structures that can be lithographically useful. Till then.